Okay, so welcome to the video on the next part of pre-calculus, which is 0.3 day 1 characteristics of quadratic functions. So now we're going to kind of, put the trig stuff away for a while, and we're actually going to do something that might seem a bit more like math that you might see in an Algebra 1 or Algebra 2 class. We're going to review something called quadratic functions from Algebra 1 or 2. So let's begin on that. Alright, so here our do first is for the parabola shown below with the vertex -2, 3, determining the missing coordinates for each of the labeled points. Be prepared to share your reasoning with the rest of the class. So basically here we're just kind of guessing where these points are based on the information given to us here. So there's no real right answers to this. We're just kind of guessing here and deciding what points have here. So what I'd like you to do for a second is just pause the video and try to guess the missing points here based on the information you see. So just pause the video for a second, write some numbers in there and see what you get. Okay, so I'm assuming now you've paused the video. So let's start with this point. So first of all, we see that this point, this is our x-axis right here, and this is our y-axis. So this point actually hits the x-axis, or what we say intercepts the x-axis. So at that point, we know that the y has to be 0. And what is the x-coordinate? Well, again, we're not told exactly, but we know it has to be -2 and -8, and I kind of guessed here that that was -4. So again, just you want to get kind of close to that. And again, that's what we call a x-intercept. Right, because it's interacting with the x-axis. All right, let's look at point B. Well, that point actually is touching the y-axis, so we know that actually has a 0 in the x. This is what we call our y-intercept, and it has to be somewhere between 0 and 3. So it kind of looks like maybe 2. So we'll just put a 2 there, and so 2 would be what we call our y-intercept, because again it intercepts the y-axis there. C is another x-intercept because, let's see, so 2 is about right here, and then 0 is on the line, so it's probably about 1 in the x-coordinate, and again it has to be 0 in the y. D, it's going to be a little past 1, so it's going to be below, so we know the y has to be negative. I guess -3, but I could see an argument for maybe -2. The reason I say 3 is it's because it's about the same distance here that it is from the x-axis here. So I guessed about -3. And then E, well, for E, we can see that that is 9 below, and the distance is a little bit further than 2. Maybe it's about 4, so I guessed 4 in the x. So again, those are some guesses on my end, but you feel free to give whatever interpretation you would think. So now we're going to talk about quadratic functions. And what exactly are quadratic functions? Well, you've definitely seen them. You've worked with them probably before in a Algebra 2 class. And they're actually going to become even more important in pre-calculus. We're going to dive a bit more into what they mean. So let's review them. So basically what we're going to say is a quadratic function, spell this right, yes, function, is a function of the form f of x, so remember f of x means this is a function, is equal to ax squared plus bx plus c, where a, b, and c are just numbers, right? They could be 2, 3, whatever. Let me go ahead and give you an example here. So for instance, we could have a function g of x that's maybe like 2x squared plus 3x plus 4. That would be what we know as a quadratic function, right? That would be a quadratic function. So a few things about the quadratic functions. Let's talk about what it maybe looks like. So a quadratic function has a very familiar shape. You might have, again, seen it before. It has this sort of, some people describe it as a bowl. So it's going to kind of look something like this, right? So maybe something like that. If I were to graph that on my calculator, that's what I would get for a quadratic function. Now there's a few things about this quadratic function. Let me make the x and y plane here. a few things about this quadratic function that we should know. The first is that this point that hits the y-axis, that's what we're going to call the y-intercept, right? And again, the way I remember y-intercept is think about football, right? In football, an interception is when the defense, catches the ball or intercepts the ball from the quarterback. So, all y-intercept is where the quadratic function intercepts the the y-axis, right? And the way that we can actually know what the y-intercept, where it's going to hit on this point, is if we look at the last number c. So c actually is always going to be our y-intercept. Okay, the next thing we notice on a quadratic function is the fact that we can actually kind of split it in half here, right? And it's almost symmetrical, right? It's almost like over this line, it's like this part of the function is looking at a mirror. So this line is actually what we call the axis of, not evil, but of the axis of symmetry. The axis of evil. The axis of symmetry. And also, you'll notice every parabola will always have a lowest or highest point, a point where it kind of changes direction. And we're actually going to call this point the vertex. And a vertex is kind of where something begins and ends in regular language. But again, that is going to be called the vertex, is the point at which the parabola kind of sprouts from. Oh yeah, let me mention this too. You'll notice I've said this a few times, but yeah, this particular shape, we know that as a parabola. It kind of sounds like bowl, right? Because it kind of looks like a bowl, so we call it a parabola. Now, there's some ways that we can actually look at the function of a quadratic and determine what these are on the graph, right? We can actually use this information given to us in the function and actually draw the graph. The first thing is that if I want to know what the axis of symmetry is, what I do is, well, I'm going to say x is equal to, because anytime I have x equals to a number and I enter that into a graph, that's going to give me a line that goes straight up and down. That's going to be equal to negative b over 2 times a. So I take the number in front of the x and I divide it by 2 times a. And also notice there's a negative built into this formula. So anytime you're filling this in, don't forget there's a negative out there. Let me give you guys a quick example. So say if we have this one up here and we're looking for its axis of symmetry, well, we're going to say x is equal to negative. We take the number b here in front of the x, 3 over 2. And that's what we would call, 2 times 2, sorry. And that's going to be negative 3 over 2 times 2, which is 4. So the axis of symmetry would be at negative 3/4. Now our vertex, if you'll notice, the vertex is actually a point in space in the xy plane. So we're actually going to need to do the ordered pair thing where we need both an x and y coordinate. And the x coordinate of the vertex is actually just the axis of symmetry, because you'll notice it runs right through it. So once we find the axis of symmetry, we actually know the x coordinate of the vertex. And once we know the x coordinate of the vertex, we can just enter whatever number this is into the function, and that will give us the y coordinate of the vertex. So that's how we find both our axis of symmetry and vertex. They're very related to one another. Okay, so now that we've kind of described what those things are, let's actually do them in a problem to kind of help us comprehend those terms. So here we have a problem that says use the axis of symmetry, y-intercept and vertex to graph x squared plus 2x minus 3. So how are we going to do that? Well, it's actually pretty simple. The first thing we want to do is let's actually look for the y-intercept, because all we have to do to find the y-intercept is look at this last number on the function, which is negative 3. So we now know that the y-intercept is equal to negative 3. And that's it. If we're ever asked what the y-intercept is negative 3. And again, we can graph that on our graph. At negative 3, we know that that graph should go through this point. Okay, let's find our axis of symmetry. So again, the formula is going to be x is equal to negative b, where this is our b, a, and that was our c. So we're going to say negative. Remember, there's a negative built into the formula. So we're going to say negative 2, because the 2 is in front of the x. Now a, we'll notice there's no number in front of there, but remember, anytime there's not a number in front of a variable, we just assume that it's a 1. So what we're going to do is we're going to say 2 times 1 in the denominator there. And of course we can reduce that. Negative 2 over 2 times 1. 2 times 1 is just going to be 2. That's going to actually be just negative 1. So now we know that our axis of symmetry is x is equal to negative 1. Meaning that we're going to, this parabola is actually going to reflect across this line, this vertical line on negative 1. So I'll draw like a little dotted line to represent that down negative 1. So how do we find our vertex? Well, part of it is done for us because, like I just said, the x-coordinate of the vertex is where the axis of symmetry. So it's going to go from here. So we know the x-coordinate of our vertex is negative 1. And all we have to do to get the y is take that x and just plug it into our function. So we're just going to say f of negative 1 is equal to negative 1 squared plus 2 times negative 1. So wherever we see an x, we're going to plug in negative 1 instead of x minus 3. Okay, negative 1 squared, well, 1 times negative 1 should give us a positive 1. 2 times minus 1, that's just negative 2. And then minus 3. 1 minus 2 is negative 1. Minus 3 is negative 4. So that means that our vertex is at negative 1, negative 4. So we look at negative 1 on the x and negative 4 on the y, and that point is there. And now we just kind of have to play connect the dots, right? We just have to say, okay, well, we know it's going to start from here, and it has to hit that y-intercept, so we'll draw something like this. And again, it's going to reflect, so we want to create that shape. And we're done. We've drawn our graph based on just what we found from the axis of symmetry and the vertex. And that's it. Let me go and write this in so that I'll be very clear. That's our vertex. This is our axis of symmetry, that line. And this is our y-intercept. You don't have to write this in every time. I'm just kind of being really explicit here so people understand what I'm talking about. Let's do another example together. So here we have, use the axis of symmetry, y-intercept, and vertex to graph this function. Okay, same thing. We look at this last number to get our y-intercept. That's usually the easiest to do first. So it's just 5. So we know it's going to go through 5 on this graph. So right here. We know that our axis of symmetry is going to be x is equal to, so again, we need a negative in the top. Now notice we have a minus 4. So what we're going to have to do here is I would recommend putting it in parentheses and noticing that this negative is coming from the negative 4 in the function. And we're going to divide it by 2 times the number in front of the x squared, which is just 2. So negative 4 times negative 4, well, that just gives us 4. Or sorry, negative times negative 4. And 2 times 2 is 4 as well. And that just gives us a friendly axis of symmetry of 1. So that means we're just going to create a dotted line down 1 here. That's our axis of symmetry. And our vertex, again, we already have our x-coordinate of the vertex. We know that it is 1 in the x-coordinate. And to get our y, we just plug it into the function. 2 times 1 squared minus 4 times 1 plus 5. 1 squared, well, that's just 1. And then we have a 2 in the front. 4 times 1 is, of course, minus 4 plus 5. 2 minus 4 is negative 2 plus 3, or sorry, plus 5 is going to give us 3. So that means our vertex is going to be a x1, y3 right there. And then we just kind of again, it sprouts from there, so, and it has to hit that 5. So it's going to look something like that. Alright, so now that I've done those 2 examples, why don't you pause the video and try number 3 and 4. If you're still struggling to understand this concept, try number 3, because that's generally an easier one, follows from a lot of the stuff we've already done. If you want a bit more of a challenge, you feel like you understand this, try number 4. This one's not too much harder, but there's some nuances to it that we should that make it a little bit more difficult. So go ahead and pause the video and try those 2 out. Okay, so I'm assuming you've gone through these and worked through them a little bit, so let's talk about them. So same problem. Again, first thing, let's figure out what the y-intercept is. It's just the number over there. It looks like it's just 5. Okay, and we want to draw that on our graph. 5 is up here. Our axis of symmetry, again, we just use that formula. X is equal to negative the number in front of the x, which is 6, 2 times the number in front of the x squared. Again, there's no number there, but we're just going to assume that's a 1. And negative 6 divided by 2, well, we know that that's just going to be negative 3. So our parabola, or our quadratic function, is going to reflect across this line here. And our vertex, again, we already know the x-coordinate is what the axis of symmetry is, which is negative 3. And we can just plug that into our function to get what is the y-coordinate. So plus 6 times negative 3 plus 5. Negative 3 squared is 9. 6 times negative 3, that's negative 18 plus 5. 9 minus 18 is negative 9 plus 5. So let me write that out a little bit more. That's going to give us negative 4. So our y-coordinate of the vertex is negative 4. So we go to negative 3, go down to negative 4 to right. And again, these two have to connect, so we know it's going to do something like that. And then the other side, it has to reflect across that axis of symmetry. So there we go. That is our graph. Okay, let's go on to number 4. So this one's a bit more difficult, but it's not too bad. We just have to do a bit of thinking. For this one, we have to recognize that there is no c term. So what is our y-intercept? Well, we could think of, well, if there's nothing there, we could think of it as a plus 0. There's nothing there. So that must mean our y-intercept, or where this function is going to run into the y-axis, is at the value 0. So that means on our y-axis, where it's going to run into, that's here at 0, or some people might call it the origin, right, where both the y and x intercepts interact. We're going to say the axis of symmetry, again, we're going to say x is equal to negative. Again, remember there's a negative 2, so you actually have to write the negative twice because there's a negative in the formula and the negative 2, divided by 2 times the number in front of the x squared, which is 3. Negative negative gives us positive 2 over 6. And we want to reduce that a little bit. That's going to give us 1 over 3, which is a fraction. So we don't get to write this at a friendly whole number, but it's not too bad because 1/3 we could just think, well, if I split up the distance between 1 into 3 pieces, it's going to be the first one, 1/3, so we'll just write our axis of symmetry right here. That's 1/3. And then we want to plug this in to get our vertex. So our vertex, again, we know that the x value is going to be 1/3. We know that our y, well, let's figure it out. F of 1/3 is equal to 3 times 1/3 squared minus 2 times 1/3. And you'll notice this is a bit more challenging because we don't have friendly whole numbers this time, but what's nice is we don't have a y-coordinate to add to it, so we don't have to mess with that. So you can enter this into your calculator, but I'm going to kind of work with this a little bit. So remember your PEMDAS, which is that you have to do the exponent first. And when you square a fraction, you actually have to square both the top, the numerator, and denominator. So this will give us 3 times 1 over 9. And whenever you multiply a whole number by a fraction, you're just going to multiply the whole number with the numerator. So this is going to be 2 over 3. Let's see. We can actually do this because, again, we multiply 3 and 1. That's 3/9 minus 2/3. 3/9 is going to reduce to 1/3. And, of course, we have a third and we take away 2/3. It's going to give us negative 1/3. So our y-axis, or sorry, our y-coordinate is negative 1/3. So, again, that's going to be like, you know, 1/3 of the way to negative 1. So about right there. And so, again, we want to connect the y-intercept and the vertex. So this side will look something like that. And then this will sprout out in the other direction. So that is that problem. Okay, so hopefully what you've noticed is all of these graphs, there seems to be some point at the bottom that it kind of bottoms out, right? That's like the bottom point of the graph. So what we're going to do here is we're going to talk about that and talk about what are called maximum and minimum values. So let's talk about that. Let's talk about max and minimum values. And that's pretty much exactly what it sounds like, right? Maximum and minimum values. That basically just means that where the function is either at its peak or at its lowest. So if we're talking about a max, how can we distinguish the two? Well, again, remember, a quadratic function is going to always look like this. And how do we know whether the function is a maximum or min? Well, first of all, if the number in front of the x squared is positive, so if it's greater than 0, then we know that the graph will have a minimum. So for example, I drew a little xy plane here. We know that this function is going to look something like this. Like that. And we know that this point right there, the y-coordinate of that point actually is our minimum value. That's our minimum. And what about, well, when would something have a maximum? Well, if the number in front of the x squared is less than 0, if it's negative, then we know that our graph is going to look something like this. It's going to have a negative value, meaning it's going to kind of, instead of looking like a bowl like they usually do, it's going to look kind of like a hill, kind of like this. And again, we'll say that the maximum is right there. Now, if you'll notice, that actually occurs at the same point as the vertex. So the minimum, actually, we can figure it out by actually just looking at the y-coordinate of the vertex. And same thing over here. All we have to do is look at the y-coordinate of the vertex, and that gives us whatever our maximum or minimum value of the function is. So now let's go ahead and try this out. So it says determine whether each quadratic function described below is a maximum or minimum value, then find the value of the maximum or minimum. Alright, so first of all, let's determine whether it is a max or min. So we see here that there is a no negative in front of the x squared. Again, if there's nothing there, we just assume that it is a 1. And all we have to do is look at that number, and that number looks like 1 is, again, a positive number. So that here we're going to have a minimum value, meaning it's going to kind of bottom out. So how do we find the value of this maximum or minimum? Well, first of all, let's use our axis of symmetry formula to get our x-coordinate of the vertex. That's going to be, again, negative 2. The negative, again, is built into the formula. That's where it comes from. And then we say 2 times 1, which is the number in front of the x squared. Negative 2 divided by 2, that's just going to give us a negative 1. And I'm going to actually draw this one out here. That's our axis of symmetry. You might notice this is familiar. And again, the vertex, so the vertex, we just have to look at we already know the x-coordinate is negative 1. The y-coordinate, we just plug it into our function. Negative 1 squared plus 2 times negative 1 plus minus 3, excuse me. And again, we've actually already done this problem. I wanted to do one again to show you see if you're paying attention, but also just, so we can learn the same concept with the same equation. 1 minus negative 2 is negative 1 minus 3 is negative 4, as we got before there. So that's going to bottom out here. And we could even draw it out a little bit. And again, you could even say the y-intercept is at negative 3, so we know it's going to look something like this. And okay, notice this point right here, this negative 1, negative 4, the vertex, this negative 4 is what we call our minimum value of this function, meaning that the negative 4 is the lowest value that we can actually get out of this function. We can't plug in any number other than negative 1 to get the lowest value, which is negative 4. The lowest value you can get out of this function is, in fact, negative 4. Okay, so let's go on to number 2. Okay, so I kind of messed up here because I didn't really make this interesting. If you'll notice, if you're paying attention, that all of these have positive numbers in front of their x squared. So let's go ahead and make that negative 2x squared minus 4x plus 3. It won't change much. Well, now that I've placed a negative in front of it, that must mean if it's a negative 2 in front of the x squared, that makes it a maximum. And then I just go through the procedure. I find my axis of symmetry. I'm going to say x is equal to negative. Again, use the b, negative 4. Remember that it is negative there. 2 times the number in front of the x squared, negative 2. Negative 4 is 4. 2 times negative 2 is negative 4. And 4 divided by negative 4 is going to give us negative 1. Now to get our y-coordinate of our vertex, we just plug it into the function. We just plug the x value, because remember our vertex has an x-coordinate of negative 1. So we'll say 2 times negative 1 squared minus 4 times negative 1 plus 5. Again, you can always enter this into your calculators, guys. I'm not against you doing that, but this really is some simple math. Negative 1 squared is just positive 1, so that's just 2 there. Negative 4 times negative 1 is positive 4 plus 5, and that's going to give us 2 plus 4 is 6 plus 5 is going to be 11. So again, because this has a negative in front of the x squared, we call this the maximum value. Now notice I didn't graph this, and most of the time if you're asked for the maximum value, you're typically not going to be asked to graph the function. I just did that in the first problem to kind of give you a better visual description of what's going on there. But so that's how we get our maximum value. That's the highest value you can get out of this function. Okay, so go ahead and try numbers 3 and 4. What I'd like you to do though is let's go ahead and change the in front of x squared here. Let's make that negative to make it interesting. So remember that's negative x squared minus 5x plus 6. Give that a shot. Okay, so let's work through this one. So again, because I put that negative in front of the x squared, that's going to make this, it's going to have a maximum value. And again, we find the axis of symmetry, which would give us the x-coordinate of the vertex. That's going to be negative 5 in the top with the negative in front built into the formula, times 2 times, again, because I put a negative there, that's going to make that negative 1. So if there's a negative in front of the x squared, you still assume there's a 1 there, but that means that's a negative 1. That's going to give us negative 5. 2 times negative 1 is, of course, negative 2, which is going to give us negative 5 over 2. And to get our y-coordinate of the vertex, which would be the maximum point of this function, we just plug that into the function. So negative 5 over 2. And we just plug it in. We say, let's see, negative 5 over 2 squared. Remember, actually, the negative is negative 5 over 2, and there's a negative outside. Minus 5 times negative 5 over 2 plus 6. Now, when you square this, remember you have to square the top and the bottom, and the negative will go away inside, but there is still a negative on the outside. So you actually have to say negative 5 squared, which is 25 over 4. plus, again, these two negatives are going to become a positive. Again, if you were multiplying a whole number by a fraction, multiply the number by just the numerator, so that's 25 over 2. And then we're going to say plus 6, which is hanging out on the end there. And again, this is probably one that you're going to want to enter into your calculator. You could try getting the common denominator across these, but entering your calculator is fine. You're either going to get 12.25. If you want to do the fraction one, I didn't do that one, but I'm going to do it right now for you guys because I love you guys that much. That's actually going to be 49 over 4. So either answer is fine. This one's in fraction form, but again, these are our max values, the highest values that this function could possibly be. Okay, let's look at the next one. So here we have x squared minus 8x plus 6. What do we do here? Same thing. Again, notice the number in front of the x squared is a positive 8, so this function is going to have a minimum value. So we say x is equal to negative. Again, notice the negative is built into the formula, so we have to put negative 8 inside of a parentheses, over 2 times 8. There's a few ways we can do this. We can cancel the 8s. I'm going to do this the easy way. Negative times negative 8 is positive 8. 2 times 8 is 16. And 8 over 16, 8 is half of 16, so this is going to reduce to 1/2. So that is our x-coordinate, our axis of symmetry, or the x-coordinate of the vertex. We plug the 1/2 into the function to get the y value of our vertex, which should give us the minimum value. It's going to be 8 times 1/2 squared minus 8 times 1/2 plus 6. This one actually works out nicely because when I square 1/2, that's going to give me a 4th. Whenever I multiply a whole number by a half, that actually is just going to cut this number in half. So that's just minus 4 plus 6. And again, I could either think of this as a multiplying 8 times 1. That's going to give me 8 over 4. So 8 over 4, of course, is just going to be 2 minus 4 plus 6. So that actually worked out to give us some nice whole numbers. 2 minus 4 is negative 2. Negative 2 plus 6 is going to be 4, which again is a minimum value. So 4 is our minimum value of the function, the lowest value I can possibly get out of this function. So again, why is this useful? What is the point of doing this, right? It's not that complicated, but you know, why are we doing this just for the sake of doing this? Well, let's actually look at a more applied problem here. So this problem says a batter hits a baseball with an initial speed of 64 feet per second. If the initial height of the ball is 3.5 above the ground, the function distance, so the distance over time, so how far the ball travels as a function of time, is going to be 64t minus 16t squared plus 3.5. That models the height of the ball above the ground in feet as a function of time, t, measured in seconds. Determine the maximum height of the ball. So one thing is, this kind of makes some sense, right? Because 3.5 is the initial height. And if you think about a baseball player is about 5 to 6 feet tall. So he's probably going to hit it, you know, chest or knee high. So it's probably going to be about 3.5 feet high. And 4 feet per second is actually pretty quick, right? Baseball moves off a bat pretty quickly. Now, one thing I would advise is you'll notice that the square term, the t squared, is actually in the middle. I would highly recommend rewriting it so that the t squared term is first. So get negative 16t squared plus 64t plus 3.5. So I'd recommend rewriting it in how we usually see, which is the t squared starts off and then t and then our constant or the y-intercept at the end. Okay, so we've rewritten this function. This has a negative 16 in front of it, so that means it's going to have a maximum value. And that makes sense, right? Because we're going to pop it up and then it's going to go up and then come back down, so it should have some max height that it gets to. And then we just go through the procedures like we did in the other problem. The axis is symmetry. The x-coordinate of our vertex is going to be the middle one, the number in front of the t, which is 64. Negative 64, don't forget that negative, because that's built into the formula. 2 times negative 16. Okay, so that's, let's see, 2 times negative 64, that's negative 32. And actually, 32 is half of 64, so that's going to reduce to 2, and the two negatives cancel there. So this ball is actually going to reach its maximum height at 2 seconds. And actually, I made a boo-boo here. We shouldn't actually call this x because we're talking in terms of t or time, so we'll say t is actually equal to that. But again, it works the same way. And again, our vertex, to get the y-coordinate of the vertex, we just plug this into the function. That's going to be d2 is equal to negative 16, 2 squared, plus 64 times 2, plus 3.5. 2 squared is going to be, okay, 2 squared is 4. 4 times negative 16, that's going to be negative 64. Plus 2 times 64, that's 128. Plus 3.5. That's actually going to give us about 67.5. So that means the max value at 2 seconds, the max value of this function, or the maximum, the highest point at which the ball's going to go, is 67.5 feet. So that means after 2 seconds, after it makes contact with the bat, if we want a little diagram here to kind of make it interesting, draw a little baseball player. He's going to pop it up, and after about 2 seconds, it'll reach its maximum height of 67.5 feet. Which is what I love about math, is that if we actually, figured out what the initial speed of the ball was off the bat, we actually could, and kind of measured the initial height of where the ball, we could estimate or know where the ball hit its maximum height. So that's what I really like about math, is it really does represent the physical world that we see around us really, really well, so that we can make some predictions. Alright, so I hope that was helpful. That was our first dive into quadratic functions. So I'll see you guys next time.